So today we're going to be discussing the atmosphere and how weather and climate are related to all of the air that's currently moving around in multiple different layers of our atmosphere. But before we can really get into this, we need to first discuss what exactly is the difference between weather and climate. So our weather, it's just what's occurring day to day. We might check an app on our phone to see if it's going to rain, what the temperature might be, or what the humidity is going to be. So weather happens over a really short period of time. It's constantly changing, not only day to day, but even hour by hour. And this is very different from our climate. Our climate is looking at something over a very long period of time. So it's just our general weather. So if I were to talk about the climate of Florida, for example, I might say that it's hot and humid. That does not mean that in February it might not get cold, or there might be a period of a year where it gets fairly dry. But if we're looking generally at what the weather is like over a long period of time in our state, it's almost always going to be hot and humid. So we're going to see that climate is basically a very long-term average of our weather. But there are going to be a lot of different things that are going to affect not only our weather, but since climate is a long-term average of our weather, it's going to affect our climate as well. So if we do pull out the apps on our phones to figure out what the weather is going to be like today, there are some different things that we might want to know about. The first of which is just what's the temperature of the air? We're going to dress differently if it's 30 degrees or 70 degrees outside. But we might also want to know about the humidity. How much water is being held in the air? So, at least for me, when it's really humid outside, my hair acts totally different than just on a normal day to day. But if I were wanting to spend some time outdoors, I would want to know how much cloudiness there will be, how many clouds will be in the sky to determine how much sunlight I'm going to get, and also what kind and the amount of precipitation. I want to know if there's going to be a huge hailstorm. I definitely don't want to go outside. But if there's going to be a slight sprinkle, I might just take a jacket and go anyways. And the last couple factors we might not care about, but they're still really important for our weather. The first of which is the air pressure. How much is the air either squeezed in or separated out molecule by molecule? And here we're going to see that the air pressure is going to determine not only how fast the wind is blowing, but also which direction the wind is going to blow in as well. If we were to look at our weather over the entire year, at least for the northern hemisphere where we live, we'll see that in our summer months, the temperature outside is going to be hotter than during our winter months. So here in this chart, the months are just abbreviated here on the x-axis. January, February, March, April, etc. So we're always going to see that in our summer months, like June, July, and August, we have higher temperatures than we do in January and February, and then November and December. But each month we also see record highs and record lows for that month. So a record high is just going to be a day where it's hotter than the rest of the month. And a record low is just going to be a night that it's cooler than the rest of the month. But generally, we're also going to see, if we just look at our averages here, that during the day, it's hotter outside than it is outside at night. This is all just differences in whether or not we're receiving any energy or heat from the sun. So when we're talking about our atmosphere, we want to be concerned with the types of gases that make up our atmosphere. So this is basically just air. Air is a mixture of multiple gases. When we think about air, we probably first think about oxygen because that's what we need in order to breathe. But just in general, around our planet, most of our air is not oxygen. 78% of our air is made up of a gas called nitrogen. So when we breathe, nitrogen isn't something that we actually need in order to survive. But things like plants do need this nitrogen. Our second most abundant gas, however, is oxygen. which sits at 21%. And this 21% is super important. If it were to increase 2%, let's say that the oxygen in our atmosphere is now 23%. Even with that slight increase in the amount of oxygen, we're going to see that we would all start spontaneously combusting. We would just randomly catch on fire because we would have more oxygen in our atmosphere, which is the gas that's necessary to keep a fire going. Now, on the other hand, if our oxygen levels drop 2%, if we were suddenly down to 19% oxygen in our atmosphere, we would all suffocate because there wouldn't be enough oxygen for our lungs to supply the necessary gas to all of the necessary tissues and organs within our body. But although these two gases together make up 99% of our air, there are lots of other gases that are found in our atmosphere. But these gases are found in really small concentrations. So we're going to see that almost 1% of our atmosphere is a gas called argon. And argon was found in that very last column to the right side of our periodic table. It's a noble gas, which means that its entire valence electrons are full. So it's not going to react with anything. So living organisms don't really use argon. It's just present inside of our atmosphere. But that tiny little sliver of yellow here, all these other gases that are found, we're going to find not only other noble gases, such as neon and helium, but we're going to see a lot of greenhouse gases, things like methane and carbon dioxide. And these greenhouse gases are actually what is currently changing our global climate today. But within our atmosphere, we're going to see that a small proportion of our air is going to hold water vapor. So this is just the gaseous form of water. If you take a really hot shower, you're going to notice that your bathroom probably fills up with steam. This is just water vapor. It's that gas form of water just stored within the air. But this water vapor is going to be really important, not only for our atmosphere, but for our hydrologic cycle as well. Because when this water vapor condenses, it's going to form clouds. So if we were to go outside and watch the clouds flow by, we're actually just watching the water move around inside of our air. But eventually those clouds are going to be saturated. They're going to be completely full of water vapor, and then some form of precipitation is going to happen. Might be rain, snow, maybe even sleet or hail. But that water vapor is going to leave the clouds and fall to the surface. And while we need water vapor in our air, it not only keeps our skin hydrated, but our lungs hydrated, and keeps our water cycle going, this water vapor is also a greenhouse gas. That means that it's collecting some of the heat coming from the sun and keeping the surface of the earth warm. But this is one of our greenhouse gases that is natural. We need to have this greenhouse gas in our atmosphere. On the other hand, we're also going to see something called aerosols in our air. And these are tiny, like nanoparticle size, either solids or liquid particles. And these aerosols are going to be really important because it's going to allow this water vapor to collect on top of these little particles. So, for example, if we were to have an aerosol, we just have a tiny little particle in our atmosphere. This means that water vapor is going to be able to condense around the solid. That water vapor is going to be able to completely wrap itself around it and use it as a condensation nuclei. It's going to be able to condense around that aerosol particle. But these aerosols are also going to be really important when it comes to our climate. So they're going to act kind of like those visors that you might see in the windshields of certain cars. Those visors are meant so that if you put them in your windshield, when the sunlight comes in, it's going to hit that visor and then reflect right back off your windshield. That sunlight is not going to enter into your car, hopefully keeping it a little bit cooler. These aerosols act the exact same way. So when there are a lot of aerosols, these tiny little particles in our atmosphere, they're actually going to take the sunlight coming in and it's going to cause that sunlight to be reflected straight back out into space, which can help cool off our entire planet. But you've likely seen either a sunrise or a sunset. You've seen these really vibrant colors like pinks, purples, and sometimes even greens around these times of the day. This is all due to aerosols in our atmosphere. As these aerosols are causing the sunlight to reflect off of these tiny little particles, it changes the wavelength of the sunlight, causing our sky to look like it's multiple different colors. But aerosols can either be natural. Here we can see a dust storm coming off of the Sahara Desert. Just tiny bits of sand that have been pushed up into the air. Totally natural. But if we look farther down here, we can see air pollution. This is where factories or industries have been pumping out dirty air. And these tiny little particles are still aerosols, but now they're man-made. They're polluting the environment. So here we see that water vapor, totally natural. But aerosols can either be natural or they can be man-made, in which case we're going to call it a pollutant. But another part of our atmosphere that's going to vary from place to place is a gas called ozone. So when we inhale, we take in oxygen, 2 oxygen atoms, or O2. But ozone, we have 3 atoms of oxygen all connected together, or O3. So this ozone is going to be great for us. It's stored above the surface of our planet. And it's going to kind of absorb some of this really harmful UV radiation coming from our sun. So think about it as kind of like an SPF for the surface of our planet. We put on sunscreen to block some of the harmful UV radiation from being absorbed into our skin. Ozone works the exact same way. Now when this sunlight is coming in towards the surface, this ozone layer here is going to absorb that sunlight. It's just going to disappear. And that harmful radiation isn't going to reach the surface where we live. And this is really helpful because it's going to help limit the types of cancers that we see. But ozone doesn't have a uniform distribution around the planet. Back in the 90s, we developed an ozone hole over Antarctica. So this meant that the entire continent of Antarctica was getting these crazy harmful UV radiations coming down and hitting the surface. But thankfully, very few animals lived at the surface. But since the 90s, we've blocked some of these really harmful chemicals that we were polluting our air with that were causing this ozone hole. And in the decades since, we've seen that our ozone hole is slowly closing up. It's still present, but it's a lot smaller than it was 30 years ago. So now we're going to move into air pressure. Exactly how much does this air weigh, or the pressure it's squeezing down around the surface of the Earth? So this atmospheric pressure, it's basically the weight of the air. So if we were to look at our planet here, as our atmosphere changes above the surface of the Earth, we're going to see that the amount of air is going to weigh less the higher we go above the surface, which is just called our altitude. So we're going to see that if we were to start off at the surface of our planet and then slowly start increasing our altitude, we're going higher and higher into our atmosphere. We're going to start seeing less air. So if you've ever seen videos of people, say, climbing a giant mountain like Mount Everest, they have to take tanks of oxygen with them. That's because the higher they go, there's less air up there. There's just not enough oxygen for them to breathe. Without those oxygen tanks, they would suffocate because there's so little air the higher we go in our altitude. So we see that because there's less and less air, the higher that we go with our altitude, that because there's less air, that air is going to weigh less. So therefore, the higher we go, or as we increase our altitude, above the surface of our planet, we're going to see that air pressure decreases. So when we look at our atmosphere, we're going to see four different layers. So we're going to start off from the surface of the Earth and then work our way out into outer space. So the lowest layer of our atmosphere is called the troposphere, and this is where we live. So we saw that as we increase our altitude, as we work from the surface and then go higher up into the air, that we were decreasing our air pressure. We also see that as we increase altitude, we're going to start seeing that our temperature decreases as well. So the higher that we go, let's say we climb a mountain, the colder it's going to get as we keep increasing our altitude or as we keep climbing. And this is related to the environmental lapse rate. On average, we see that there's about a 3.5 degree Fahrenheit decrease in temperature with every 1,000 feet that we go higher inside of our atmosphere. So if we know exactly how high we are inside of this troposphere, we can easily calculate generally how cold it will be at that elevation. But we're going to see that the total thickness of the troposphere, from the surface to the top of the troposphere, is going to vary. But on average, it's about 12 kilometers high, or just about 7 miles in thickness. And once we reach the top of our troposphere here, it's called the tropopause. So we're going to see that between each of these different layers of our atmosphere, we're going to see something called a pause after. It's just telling us that it's a boundary. And the pause is always named after the layer beneath that boundary. So when we look at our tropopause here, it's the very top of our troposphere. So here we're just looking at the temperature changes between the top and the bottom of our mountains. Again, as we increase altitude, as we go from the surface of our planet and start going higher in our altitude, we're not only seeing that our air pressure, the weight of that air is going to decrease, we're also going to see that the temperature decreases as well. So here along the base of this mountain, we can see that there's a palm tree. Living in Florida, we know that palm trees will require warmer temperatures. But if we look at the top of this mountain here, we can see that it's covered in snow and ice. And we also know that in order to have snow and ice, we need really cold temperatures. So this photo is just showing us, again, that as we increase our altitude, to go higher on top of this mountain, our temperature is going to decrease. So this environmental lapse rate is a little variable. That means that even though on average it's about 3.5 degrees Fahrenheit of a decrease in temperature every 1,000 feet we go higher in our altitude, but it varies a tiny bit from place to place. So scientists are always testing exactly what this environmental lapse rate is like for different areas of our planet. So to do this, they just have a weather balloon. They're going to get this giant balloon and fill it with helium. Helium is a very light gas. So if you've ever been to a party with a helium balloon, these are the ones that are just going to float up to the ceiling. So these weather balloons, because they're large and just full of helium, they're going to start going up through our atmosphere. They're just going to keep rising and rising until eventually, when they get out close to outer space, and air is very limited, these balloons are going to pop. And the radiosonde, what this guy is holding here in his left hand, is a device that's going to measure the temperature as this balloon is rising up in our atmosphere. So once the balloon pops, this radiosonde is going to float back down to the surface of the Earth. And it has a GPS inside of it, so this scientist is going to be able to go out into the field and collect it and look at how the temperature changes with increasing altitude in that exact location. But that was for our troposphere. this bottommost layer of our atmosphere where humans live. As we go above this tropopause, or the top of our troposphere, we're going to enter into our second layer of our atmosphere, called the stratosphere. Here our stratosphere is going to go from about 12 kilometers to 50 kilometers above the surface of our planet. But as we go between our different layers, we're going to see that temperature is going to change. In our troposphere, we saw that the higher that we went in our altitude, the colder that temperature got. But we're going to see the exact opposite with our stratosphere. As we go from the tropopause to the top of our stratosphere, here we're going to see that the temperature is actually going to increase as we increase our altitude. That's because the ozone layer is found inside of our stratosphere. That layer of those 3 oxygen atoms all linked together that's absorbing all of that really harmful UV radiation. Because it's absorbing all of this sunlight, that means that this layer is going to get hot. So the higher that we go inside of our stratosphere, the warmer the temperature is going to be. At the top of our stratosphere, we have a stratopause. Again, just a layer saying that this is the boundary between the stratosphere beneath it and another layer on top of it. And this third layer is called the mesosphere. So with our mesosphere, this is going from about 50 to 80 kilometers above the surface of the Earth. This is where we're going to see things like meteors coming through and burning through our atmosphere. And here, because we don't have any ozone absorbing the sunlight's just going to go straight through it. We're going to see that like our troposphere, the higher that we go in our altitude, we're going to see that the temperature decreases in the mesosphere as well. The higher we go in the mesosphere, the colder it's going to be. And then at the very top of our mesosphere, we have another pause. This time, the mesopause, before we enter our thermosphere. Again, thermo just means temperature. So here we're going to see that as we increase our altitude in the thermosphere, again, we're going to start increasing the temperature. We're going to start heating up this layer. That's because there's no real boundary to the edge of our thermosphere. It's gradually just going to enter out into open space where there's no air. So this means that this is the first layer of air that sunlight hits before it starts going towards the surface of the Earth. So the higher that we go in our thermosphere, the more sunlight that air is receiving, the warmer it's going to be. But here, because this is the outermost layer of the atmosphere, as the Earth is spinning around, this layer of our atmosphere is going to be spinning very, very fast. And if you've ever seen videos of auroras, like the northern lights, where you might see green kind of dancing patterns in our sky, these auroras develop in the thermosphere because we're having the interaction of sunlight and air in this very outermost layer of our atmosphere. So now with this, we're going to move more into weather, see how things like temperature changes throughout the year. So we're going to see that our Earth is not only rotating out in space around the sun, it's also rotating on its axis. This means that the Earth is constantly rotating. So with our planet, we're going to see that it doesn't just sit still in space. Instead, it's going to spin around on its axis. It's just going to spin around in place while being tilted. And this rotation takes 24 hours to complete. That's why our day is exactly 24 hours long. But because the sun is going to be illuminating part of the Earth, we're going to see something called a circle of illumination develop. The sun is only going to be able to light up one half of the Earth at a time, whatever part of the Earth is facing the sun. So while it might be sunlight here in America, that means that on the opposite side of the world, like in China, it's going to be dark at that time period. But the Earth is not only just spinning out or rotating on its axis, it's rotating and spinning around the sun the entire time, which is called an orbital motion. So the entire time that we're spinning on our axis, we're not sitting still. We are rotating around the sun. And this is going to result in our seasons. We're going to see that the sun's angle, the exact angle of whether it's hitting the Earth at a 90-degree angle or if it's coming in and hitting the Earth at an oblique or a low angle, it's going to result in our seasons, as well as exactly how much daylight, how many hours of sunlight are we receiving every single day. So we're going to see that because of the tilt of the Earth, we're going to have a really complex relationship with our sun. So if you're to look at my globe, you can see that the North Pole and the South Pole, they're not actually right on top of each other. So instead of being directly like this, our Earth is actually tilted about 23.5 degrees. This means that throughout the year, we're going to be receiving different amounts of sunlight at different places along the surface of the Earth, whether we're here at the equator, at our north, or at our south pole. So when we think about noon or 12 p.m., we're going to see, or at least think, that the sun is going to be directly above us in the sky. But actually, throughout the year, the sun is going to be in different parts of our sky. With the exception of summer, our sun is never going to be directly overhead, right above our heads if we were to look straight up. Instead, it's going to be kind of off to an angle. Still going to be in the sky, but it's not going to be directly overhead. So if we look here during where we are right now in our year, our sun would not be directly over our heads, but instead it's going to be off at a low angle, still in the sky. But as we move towards winter, we're going to start seeing that the sun is going to be a lower and a lower angle in the sky. And this is going to be really important. So think about having a flashlight. If I were able to shine a flashlight straight down on a piece of paper, that beam coming from the flashlight is going to be kept in a really small area. And it's going to be circular, like we can see here in this image. Sorry? But if we were to start changing the angle of that flashlight, if now instead of having my flashlight come straight down on my table, instead I have that flashlight coming down at a low angle, that flashlight beam is going to be over a wider area. Instead of being a little circle, now it's going to be a long oval. So we're going to see that because of the tilt of our planet, throughout the year we're going to receive different amounts of sunlight, different amounts of light, and therefore energy coming from the sun. So again, all of this is due to the tilt of the Earth. Here we can see, again, the North and the South Pole are not actually right on top of each other because our planet is tilted 23.5 degrees. But our axis, the tilt of it never actually changes. So we're going to see that this 23.5 degree tilt, instead of the Earth being straight up and down, it's going to be tilted now. But this tilt is always going to be in the exact same direction. So we're going to see that as the Earth starts orbiting around the sun, we're going to get different amounts of sunlight throughout the year. And this is what causes our seasons. At least in the northern hemisphere, our seasons are hottest in the summer, coldest in the winter, and our springs and autumns are right in between summer and winters. But we're going to see very special days developing throughout our year. And these are either going to be our solstices, which happen in the summer and the winter, or our equinox, which happen in the spring and the fall. So if we were to look at our planet, we're going to see that there are different locations, different latitudes. Right along the center of our planet is the equator, which is 0 degrees latitude. But if we were to go 23.5 degrees north of our equator. Now we're going to be sitting at the Tropic of Cancer. So during our summer, we're going to see that, let's say that this candle is going to be my sun. Now, because the northern hemisphere is tilted towards my sun, that means that during the summer, the northern hemisphere, the top half of our planet, is going to receive more sunlight. So here we're going to see that flashlight beam, that sunlight coming straight from the sun, it's going to hit at a 90-degree angle with the Tropic of Cancer, right here at 23.5 degrees north. But in the winter, again, our sun stays still while our Earth rotates around. So now in the winter, my southern hemisphere is tilted towards the sun. That means that during our December solstice, our winter solstice, on December 21st or 22nd, the sun's angle that's coming down and actually hitting at 90 degrees, creating that small area of sunlight. Now it's going to hit at 23.5 degrees south of our equator, which is called the Tropic of Capricorn. But we're also going to see two other special days throughout our year that are called equinoxes. We have one in the spring in March and one in the fall in September. So here the tilt of the Earth isn't actually going to be important. We're not going to see that part of the Earth is tilted towards or away from the sun. Instead, the Earth is going to be receiving equal amounts of sunlight. So during these equinoxes, we're actually going to see that the sun's rays are going to be most concentrated around our equator, or 0 degrees latitude, right along the center of the Earth. So this equinox is really important because equinox means equal. So these 2 days of the year, we're actually going to see 12 hours of sunlight, 12 hours of darkness. So the overall length of our days is just dependent not only where we are, which latitude we are. Again, 0 is going to be the equator, the center of our Earth. We can either increase north to 90 degrees or south to 90 degrees at our poles. But as we start increasing towards the poles, we're going to see different amounts of daylight, just the number of hours that we have sunlight. If you've ever seen this really bad horror film called 28 Days of Night, it followed this Alaskan village where vampires would go because for an entire month it was pitch black outside. Horrible movie, but at least scientifically it's accurate. Because if we start looking at places that are really high in latitude, getting closer towards our poles, we're going to see that there are entire periods of time where it's going to be light all day, or it's going to be dark all day. They're not going to get any sunlight at all. So if we were to go to the North Pole, for example, there's going to be 6 months out of the year where they never see the sun set. There's also going to be 6 months out of the year that they're not going to see any sunlight whatsoever. But on our equinoxes, it does not matter where we are on the planet. We're always going to see equal amounts of sunlight. 12 hours of light, 12 hours of darkness. So now we're going to talk more about our climate. And this is going to require us to talk a little bit about our greenhouse gases. So our planet gets all of its energy as incoming radiation from our sun. So our atmosphere, the air surrounding our planet, is basically transparent. This means that the sunlight and the heat coming from our sun is going to be able to just very easily move through the air. But because our atmosphere is not only just air particles, there's also solid and liquid particles inside of our atmosphere. We're going to see that some of this radiation, the sunlight coming from the sun, is just going to be scattered. It's going to be reflected back out into space. We're also going to see that parts of our planet is going to absorb some of the sunlight. So our clouds are not only absorbing the sunlight and those harmful UV rays, but they're also going to be taking some of the heat in as well. But we're also going to see something called albedo. We're going to see that some of the sunlight is going to come in and be reflected straight back into space. Again, just like those sun visors within a car. So we're going to see that overall, the majority of the sunlight that's coming from the sun is actually going to come down and actually reach the surface of the Earth, or at least near the surface of the Earth. And overall, about 50% of our sunlight is going to be absorbed, warming up the rocks and the water on our surface. But this albedo, the percent of light reflected, is going to be dependent on how light or how dark a surface is. So think about having to do like yard work in the middle of the summer. If you were to wear a white shirt to do this, the sunlight is going to be reflected off your shoulders. It's going to keep you a little bit cooler. But if you were to wear a black shirt to go work outside, because that t-shirt is darker in color, it's going to absorb more sunlight. You're just going to be a little bit warmer wearing that darker colored t-shirt than a lighter colored t-shirt. And this is exactly how albedo works, that percent light that's reflected. So here we're just looking at two houses. We have one with a light colored roof, the other with a dark colored roof. Same kind of example of wearing a white or a black t-shirt. With the sunlight that's coming in and hitting this lighter roof, we're going to see that up to half of that sunlight is going to just be reflected off the surface. But if we look at this darker colored roof, we can see that at a maximum, only 15% of that sunlight is going to be reflected off. So here, even though these houses have the same amount of sunlight coming down on them, the differences in whether their roof is light or dark is going to have tremendous effects on their heating and cooling bills. So in the summer, this house with a lighter colored roof is going to have a lower electricity bill than their neighbor next door with a darker colored roof. And all of this has to do with albedo, the percent of light that's reflected. The lighter colored the surfaces, the more light's going to be reflected. It's going to help cool things off. But the darker the surfaces, the more light is going to be absorbed. It's going to have a lower albedo, and it's going to start warming up that surface. And this is going to be related to how much radiation our Earth is receiving. So we receive all of this radiation coming down from our sun. But again, not all of that sunlight is going to be absorbed at our surface. A lot of it is just going to be re-emitted or re-radiated from our surface. So if we look here, we can see that we have short wavelengths, very high energy sunlight coming from the sun down to the surface. But the sunlight that's been absorbed and eventually is going to be released as heat from our surface has a longer wavelength. It's just lower energy. So think about having to walk outside barefoot in the middle of the day. I personally don't want to walk on concrete barefoot because it's going to be absorbing all of this sunlight and releasing the heat into my feet. But we're going to see that different terrestrial beings, whether it's our Earth, our moon, or another planet, we have different amounts of radiation. So we're going to see that along our moon, it's going to release more heat. Therefore, our moon is going to be a lot cooler. This is because there's no atmosphere around our moon. Therefore, there's no greenhouse gases. These gases trapping the heat along our moon. But if we were to look at a place like Venus, Venus has a whole lot more greenhouse gases than the Earth does. This means that as the sunlight is being absorbed at the surface is going to try to release some of that sunlight as heat. But because there are so many greenhouse gases in our atmosphere, it's going to trap all of that heat inside of the atmosphere or all of the air surrounding Venus, which causes Venus to be about 400 degrees hotter than the surface of our planet is. The more greenhouse gases in our atmosphere, the more heat that's going to be trapped inside of this air, therefore warming up that planet. So currently we're seeing a lot of talk about climate change. We're seeing that overall our planet is slowly starting to warm up. And again, this is due to those greenhouse gases. We're going to be see gases like CO2 or carbon dioxide. Carbon dioxide and most of these greenhouse gases are released by burning fossil fuels like coal, gas, and petroleum. All of these are actually formed from fossils. They were formed from things that used to be alive millions of years ago, hence the name fossil fuels. But because they were alive, they were organic. That means that they were full of carbon. So as we burn them, we're releasing this carbon back into our atmosphere. And it's going to trap all of this radiation inside of our air, heating up our planet. So we've seen that in the last 200 years, because of industrialization, not only have factories developed, but now a lot of people have their own cars and we drive a lot. We're seeing that the carbon dioxide levels around our entire planet are increasing. So we see that roughly every 100,000 years, we're going to see a cycle in our climate. It's going to get a little bit warmer or a little bit cooler than normal every 100,000 years. So this chart is just showing us how this carbon dioxide has changed over the last 800,000 years, almost a million years of our history. We can see that the carbon dioxide levels naturally fluctuate. But if we look at our recent past, just 5 years ago in 2015, you can see that the amount of carbon dioxide is higher in our atmosphere than it's been over the last 800,000 years. And this is all due to the fact that we're burning so many fossil fuels today. So we obviously need energy to survive. We like having air conditioning. I like being able to turn on my stove. But we're going to see that different types of energy is going to have different impacts on our climate. So if we're to look at petroleum, the gas that we put inside of our cars, this is actually the worst one of our gases that we could possibly burn. It's going to cause the earth to warm more than any other type of energy. And as we go through this list, we're going to see that each of these puts out fewer greenhouse gases. So as we go from the left to the right of this chart, things are getting greener. It's less devastating for our environment and especially our climate. So things like renewable energy, using things like our sunlight and wind to power, is actually a whole lot better than us using petroleum. Overall, the cleanest source is actually nuclear power. Nuclear power gets a really bad rap. That's because there have been nuclear power plants that have failed before. Things like Fukushima in Japan or Chernobyl in the 80s. We had these nuclear power plants fail, and it released a lot of really toxic, radioactive materials into the environment. But overall, if we're looking at how much effect that these nuclear power plants have on our climate, this is the cleanest form of energy that we can produce. So I'm a climate scientist. I've spent the last 13 or so years studying how our climate has changed. We want to study not only how the climate has changed in the past, like we saw a couple slides ago looking at the last 800,000 years, but probably more importantly, we want to know how climate is going to change in the future. And depending on our actions, we're going to see different scenarios develop. So we're seeing that right now, as we go decade by decade, from the past to today, and then into our future, we're seeing that every decade, every 10 years, that the global temperature, the average temperature around our planet, is increasing more and more each decade. Because every decade, more countries are becoming more industrialized. More people are getting access to things like being able to cool or heat up their homes, or having enough money in order to buy cars and be able to drive around. So we're seeing that every single decade, the amount of climate change is going to increase. But depending on our actions, we might be able to limit how much warming happens, or we can speed it up. So if we're to look at this chart here on the right, we're going to see these different colored lines. And these are just different scenarios. So here on the bottom, this yellow line, if we were to stop using all fossil fuels tomorrow, we no longer burn petroleum or gas. Instead, we're going to rely entirely on things like renewable energy or nuclear power. We're going to see that the climate of our planet is still going to warm a little bit, but not that much. However, if we keep burning fossil fuels like we do today, which is shown here by these blue lines, we're going to see that our planet's going to get a whole lot warmer. And then finally, as more countries become industrialized, and as more and more people are releasing these greenhouse gases by burning more fossil fuels, if we continue everything like we're doing today, it's going to follow this red line. And you'll see that by the end of our century, our planet's going to have a huge amount of warming. And this is not only going to have a huge impact on our ecosystems, but on our species as well. So humans, we take up our land. So as we start increasing the climate around our planet, there are going to be a lot of really harmful impacts for us. This top image is actually an image of what Miami will look like in the future. And this is because of rising sea levels. As our planet starts heating up, all of the glaciers around Iceland, Antarctica, and those smaller glaciers in higher elevations are going to start melting because they're going to be at a higher temperature. That means that all of that water that used to be stored as ice is going to return to the oceans. So cities that are right on our beaches are going to be the first to be completely covered in water. Miami is going to be the first city worldwide, at least first major city, that will be completely underwater. And this is going to happen by 2100. It's going to be underwater probably within our lifetimes. But we're also going to see that even if we don't live right along the coast, if we live in the center of our state, we're still going to see a lot of impacts caused by this climate change. We're seeing that every single year, we're not only seeing more hurricanes developing, but these hurricanes are getting stronger or more severe. So even though we live in the center of our state, we still feel the impacts of hurricanes. As we have more hurricanes and stronger hurricanes every single year, we're going to start seeing more destruction being caused by these hurricanes. But this is also affecting things like heat waves and droughts. If we look at California, every single year there's a drought in the summer. They just don't receive any water. This leads to those wildfires. And we saw that last summer, huge parts of California, even down to a very highly populated region like Los Angeles, were on fire. We saw that during Australia's summer, just a few months ago, that the entire continent was on fire from September to February. We're going to see more droughts and therefore more wildfires happening as our climate continues to change. But we're also seeing that our environments in general are starting to shift. Places that are cold are going to start getting warmer, and places that are warm are just going to get increasingly hotter over time. But we're going to see that depending on how close or how far away we are from the coast, we're going to have different controls on the temperature of our weather. So we see that on our planet we have something called temperature control. Think about the thermostat in a home. You might be able to set it exactly on what temperature you would like it to be. If it gets warmer in that home, the AC could kick on and help cool it off. Or if it gets too cold, the heat could kick on and help warm it up. But the Earth also has temperature control. It's going to help control the temperature in one specific place, like one individual home. But different homes have different temperatures, just like different places on our planet are going to have different temperatures as well. And it's all going to depend on how much solar radiation, how much light and how much heat are we receiving from the sun. Again, think about having a flashlight. If I have a sheet of paper and shine that flashlight beam straight, It's going to be a very small beam of sunlight. It's going to be concentrated energy. But if I take that sheet of paper and have my flashlight beam hit it at an angle, now that sunlight is going to take up a much larger area, meaning that over each individual area, like a square inch, it's going to be receiving less sunlight than if that sunlight were concentrated in a smaller area. But we also see something develop called differential heating. We're going to see that land and water heats up and cools differently than other areas. So let's imagine that we just go to the beach for the day. We're going to park in the parking lot and then walk in towards the water. If we try to do this barefoot, we're going to see that the parking lot, that land, during like a summer afternoon, it's going to get hot very quickly. If we try to walk in barefoot, it's going to burn the bottom of our feet. But even though we might only be walking 50 feet from our car to the beach, the moment that we step inside of that water, we'll instantly notice that the water is a lot cooler than the land. This is because land and water heat differently. They have differential heating. Land is going to heat up more quickly, and it's also going to stay hotter longer than water is. And this is due to something called specific heat. This is overall just the amount of energy it takes to heat up water. So if I have 1 gram of water, a specific amount of water, it's how much heat I would need to heat that water up 1 degree Celsius. And here we're looking at a map off the coast of California, the water, versus the land of California. And here, cooler colors like greens and blues means that it's a cooler temperature. Warmer colors like reds and orange means it's a hotter or a warmer temperature. So we can see the difference here between the land and the water off the coast of California. The water is always going to be cooler. The land is always going to be warmer because they have different specific heats. It doesn't take a lot of energy to heat up land, but it takes a lot of energy to heat up water. This is part of the reason why it takes so long for a pot of water to boil. So we're going to see that depending on how close or how far away we are from the coast, we're going to see very different temperatures develop throughout the year. So here we're looking at Vancouver, shown in the red line, and then Winnipeg, shown in the blue line. These are 2 cities in Canada, where Vancouver is very close to the coast. It's surrounded by water. But Winnipeg is found in the middle of our continent. There's no water around, it's surrounded by land. So here we're going to see that Vancouver, because it's close to the coast and it's surrounded by so much water, we're going to see that the difference between winter and summer. Here we're talking about maybe a 16-degree difference between our cool winters and our warm summers. And that's because the water around Vancouver is going to be absorbing some of the heat. It's going to help regulate the temperature throughout the year. But if we were to look at Winnipeg, which is in the middle of Canada, we're going to see that in the winters, it's incredibly cold. And in the summers, it gets even hotter. So now instead of seeing just like a 16-degree temperature change, we're seeing almost a 40-degree temperature change. That's because land heats up quickly during the summer, and it also cools off quickly during the winter. So if we have cities along the coast, we're going to see that overall there's not a whole lot of temperature change throughout the year. But if we live in the middle of our continent, we're going to have warm summers and very cold winters. We're going to see drastic changes throughout the season because there's no water to control how warm or how cold it gets throughout the year. But there are going to be some other really important controls on the temperature of our cities. So here we're just looking at 2 different cities. One is Concepcion, which is in the middle of the continent. The other is La Paz, which is a lot closer to the coast. Here with La Paz, it's located along a mountain range, so it's going to be higher in altitude. But Concepcion is found just on a flat, low-lying area. And as we talked about earlier, the higher that we go in our latitude or in our altitude, the colder it's going to be. So La Paz is always going to be colder than Concepcion because it's just higher in altitude. It's higher in the air. But again, we want to look at our geographic position. Is it close or is it far away from the coast? But we're also going to see that cloud cover is going to be really important. A place like Seattle, where it not only rains a lot, but there are a lot of clouds in the sky. It doesn't ever really get very warm in Seattle because here those clouds are going to be absorbing some of the sunlight. It's never going to come down and reach the rocks or the land at the surface, heating it up. And this is related to that albedo, the amount of sunlight that's going to be reflected back out into our atmosphere. If we were to look at La Paz, because it's in these high mountainous regions, there's a lot of ice and snow, which is going to help cool it off. Because snow and ice is white, we're going to see that because it's lighter in color, more sunlight is going to be reflected off the surface, keeping La Paz cooler. But Concepcion has a lot of forest. It also has a lot of concrete around it. So it has a lower albedo, meaning that the land is going to absorb more of that sunlight, heating it up. So we're just going to end today looking at temperature maps of our entire globe. So these temperature maps, we want to look at how temperatures along the Earth change. We're going to see that right along the equator, we're seeing those warmer colors, again meaning that it's a warmer temperature. And this is due to the fact that here our sunlight is hitting it at a direct angle. That sunlight is going to be really concentrated, and it's going to produce a lot of heat per square area. But as we go from our equator to the north or towards the South Pole, you'll notice that we're looking at cooler colors, which means that it's cooler temperatures. And again, this is because at our high latitudes, like our North and our South Pole, sunlight is not hitting it at a 90-degree angle. Now, that sunlight is hitting at a very low angle, meaning the sunlight is going to be spread out over a big distance, and there's going to be little energy per square area. So we can look at temperature maps of like a yearly average, but it's better if we look at them between January and July. Here, it's going to be the difference between our two extremes. In our northern hemisphere, the difference between winter in January and summer in July. And the reason we want to look at these maps is to figure out globally, how does temperature change depending on our location? So we're going to see that the warmest part of our globe is found around our tropics, right around our equator. And then as we go from our tropics towards our poles, we're decreasing the temperature. It's just getting colder. But we're going to see that these isotherms, these different lines of different colors showing the temperature, are going to shift. They're going to change their location between the seasons, depending on whether this hemisphere is tilted towards the summer or towards the sun or away from the sun. So if we're going to look at our northern hemisphere, we're tilted towards the sun in the summer, meaning that our entire northern hemisphere is going to be getting warmer. And because during the summer months like June, July, our southern hemisphere is tilted away from the sun, it's going to get a lot cooler in the southern hemisphere. But we're also going to see that our land is going to change its temperature the most throughout the year. And again, it's all differences due to that differential heating. Land is going to warm up more in the summer and cool off more in the winter than the water does. Water has a high specific heat. It's going to hold on to that temperature a lot longer. It's going to take a long time for that pot of water to boil. It's also going to take a long time for that pot of water to cool off. But if we were to go outside during the afternoon, our concrete's going to heat up a lot in a short period of time. And if we wait until maybe 7 p.m., our concrete's going to cool off. We see that land heats up and cools off a lot more quickly than water does because water has a high specific heat. So we're just going to end today looking at some of these global patterns of these isotherms, these different temperatures or different colored lines around our globe. Again, the most obvious is that the warmest areas are along our equator, coldest areas are along our north and our south pole. But now I want to look at differences between our northern and our southern hemisphere. If we look at the southern hemisphere, you'll notice that these isotherms, these lines, are a lot straighter. In our northern hemisphere, they curve around a lot. And again, this is just differences in the amount of water and land between these two hemispheres. In the northern hemisphere, we have a lot of continents. These continents are going to get hotter in the summer, colder in the winter. So we're going to see a greater change of our temperature over these continents. Our southern hemisphere, on the other hand, is mostly water. And water likes to hold on to that heat, meaning that these isotherms are going to be straighter. They're not going to change very much because most of our southern hemisphere is covered in water. But we're also going to see that our annual temperature range, the difference between how hot it gets in the summer versus how cold it gets in the winter, is going to depend on exactly where we are on our planet. And all of this is related to the amount of sunlight that we receive. If we live near the equator, there's not a whole lot of difference in our temperature between January and July. It's probably going to be 85, 90 degrees year-round because it's receiving about an equal amount of sunlight. But as we increase our latitude, as we go closer to the poles, because we're going to see places where it might be light for 6 months and then completely dark for 6 months, we're going to see very large temperature ranges. It's going to get super hot in the summer and extremely cold in the winter. And this is going to especially be true over our continents. If we were to go to Siberia, a place that's very high in latitude, but still on top of land, in our summer, it's going to get very hot, or at least fairly warm there. It might get up to like 60 degrees Fahrenheit. But in the winter, it's going to get incredibly cold. It might get down to negative 50 degrees. So here we're seeing a very large range between how hot it gets in the summer and how cold it gets in the winter.